To solve this quadratic inequality, what we're going to do is solve where it's equal to 0 and then use a graph to determine the greater than portion. So step 1 for this problem, as is with all of our inequalities, where is 2x squared plus 7x minus 30 actually equal to 0? Now we could try to guess the factors of this. Since we have a 2x squared instead of just a 1x squared, I think I'm going to use the quadratic formula. That is, a is equal to 2, b is equal to 7, and c is equal to negative 30. And I'm going to take this information and plug it into x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'll simplify this to get my answers. So the solutions are negative 7 plus or minus the square root of 7 squared minus 4 times 2 times negative 30 all over 2 times 2. I just have to carefully simplify this. So that's negative 7 plus or minus. I'll just on my calculator figure out, okay, we have 7 squared minus 4 times 2 times negative 30. So I get 289. And that's all divided by 4. And I think that square root is going to work out evenly. And it does, it's 17. So these are the two solutions. Negative 7 plus or minus the square root of 17 over 4. So if I do x is equal to negative 7 plus 17 over 4, this simplifies to, okay, that's really 10/4 or 5/2. And if we do the negative, that's x is equal to negative 7 minus 17 over 4. That's negative 24 over 4. That works out to be an integer of negative 6. So 5/2 is a solution, and so is negative 6. So on my graph, the x and the y-axis that I have over here, here's negative 6, and 5/2 is 2.5, so it's about there. What I'm going to do now is go to my graphing calculator, and in place of y1, type in 2x squared plus 7x minus 30, and see if it matches up with the two solutions that we have. Okay, I'm entering this in place of y1. I hit graph. Okay, I'm going to sketch the equation that I see after I graphed y1. So in a standard 10 by 10 window, graph comes down, goes to this spot here, passes through, it actually disappears off of the window before coming back up and going through that spot here. So again, not like a perfect sketch, but it's essentially this. I mean, I know what's really happening here is that this graph is going down to a lowest point before coming back up, so I'm sort of just going to add that in here just to illustrate what's happening. But with this picture, I should be able to solve the inequality portion of this problem. The equals is simple. It's this spot here and this spot here. We just now have to identify where this graph is greater than 0. That means where is it greater than this line? I'm going to mark that with green. That's referring to this portion of the graph here, as well as this portion of the graph here. The corresponding x values for these points are everything from 5/2 to positive infinity, but also negative 6 to negative infinity. This is my answer to the problem. The answer is negative infinity up to and including negative 6, everything from 5/2 to positive infinity. I'll put the u between there for the union, and this is the answer over here. For example 2, we have an engineer who is building a rectangular region, perhaps something like a park, that's going to be along a river. So I'm going to draw a picture for this scenario where we'll say that this is the river, and to build this, we're going to use a 3-sided fence. So we have a side here, a side here, and a side here. We're not putting in a 4th side because we want to leave it open, but either way, these 3 sides will enclose a rectangle. So if I draw that, maybe one side is shorter This side is longer, and so this must be equal to the first side I drew. And so here we go. And the thing to point out is that there is some area that this encloses. So before we even really solve this using any algebra, I'm just going to draw a couple of different configurations where we have 1,200 feet worth of material to build this fence. So there's a lot of different ways you could do this. Here's one way. Maybe this side I want it to be 100 feet long. I'm going to go ahead and put that in there. Because this is a rectangle, so if this is 100 feet long, it's got to be that this side is also 100 feet long. So I'll go ahead and place that in here. And that means that this side has to be 1,000 feet long for the sum of these three sides to equal this amount over here. I mean, said another way, if you have a total of 1,200 feet worth of material and you just used 100 here and 100 here, you used 100 twice, this side simplifies down to 1,000 feet. So there are three sides, 100, 100, and 1,000. If you want to figure out the area that is enclosed by this rectangle, you can take the product of two adjacent sides. So that is 100 times 1,000. So let's write that in here. That is a 1 followed by 5 zeros. That is 100,000 square feet. So like I said, this is just one way that you could have designed this. I think I'm going to draw maybe just one other way. So again, this is the river. And maybe this time we want to build it so maybe the sides are actually all equal. So in fact, it's a square. I mean, this would also be okay. So if this were the case, all sides, since there's only three of them, would each have to be 400 feet. So if I put 400 here, it's got to be that this opposite side is also 400. That would take us up to 800. And if you go 400 more, you definitely get to 1,200. But again, said another way, you have a total of 1,200 feet. You're subtracting off 400 a total of 2 times. The difference does give you 400 feet. So here's another configuration. The three sides are all actually equal in length. Now this time, the area that you enclose is going to be the product of this number and this number, let's say. 4 and 4 is 16, followed by 4 zeros gives us 1, 6, 1, 2, 3, 4. That is 160,000 square feet. I wanted to look at these two examples because it's kind of nice to see what's actually happening within the problem, but this one compared to this one, with respect to the area, it might be better to have this configuration here. When I used a square, we actually got a larger amount of area enclosed when we did not. So this begs the question, maybe there's exactly one way to build this fence so that you enclose the most area. And what is it? I mean, maybe it's this one that I came up with right here. Maybe it would work for a square. To verify my answer, what I'm going to do is use a little bit of algebra. I'm going to call one side of the fence x and run through this process and use a graph to figure out where the maximum area is. So let's start by drawing that picture again, where here we have the river, and we have three sides, something like this. This time when I go about it, I want to get a formula for the area, but I'd like it to depend on, I'll use the letter x to represent the length of this side. So this side we'll say is x feet. Well, if this side is x feet, this side has to be x feet as well, so I'll go ahead and put an x over here. And we should be able to determine this third side based on the variable x. And I know exactly what it's going to be. It's going to be 1,200, and I'm going to subtract off x twice. The thing is, you can't simplify it down to a number, but in terms of x, that would be the length of the side. I know it's correct because if you add x and you add x, you get 2x. And if you add it to this, the 2x and the negative 2x cancel, give you 1,200. Anyway, all this being said, you can now write the area as a function of the variable x if we just take the product of this side and this side. That is x times 1,200 minus 2x. So now we have a formula. That is something that we could graph to look at. To figure out where the largest area is would be the greatest point on the graph of this function. And I'm noticing I could distribute the x into the parentheses, so I'm going to go ahead and do that. I'm going to write this as a of x is equal to, we get 1,200x minus 2x squared. It'd be completely okay to write this with the x squared portion first. It really doesn't matter. They're all equivalent. So now I want to go to my graphing calculator to actually look at this graph, see where it's the biggest, but maybe I'll make a couple of observations first. And that is, are there any restrictions on x? Like, what's the smallest x could be? What is the largest x could be? Well, certainly, if I'm building a fence, the length of a side can't be less than 0. It's got to be some positive number. In fact, if x was equal to 0, that would just mean there is no side here or here, and you're just putting a fence right along the river. So we can't go any lower than this number. It's really meaningless within the problem. Now, the second thing is, how large or how long could this side be? You can't go forever. You got to stop at some point, and the place where you're going to stop is 600. If this side was 600, it would mean that this side has to be 600 as well, which would leave you nothing for this side, so we can't go past this value. I'll be putting equals in here, even though technically I guess we couldn't use them, just because when I look at my graph, I want to refer to those spots. So now we're going to try to graph this thing. So I want to come up with some graph for my calculator by entering this function, a of x, into y1 and choosing an appropriate window, an x-min, an x-max, a y-min, and a y-max. So I already know my x-min, I'm going to set it to be 0. I can't go any lower than that. It's got to be some positive number. My x-max, I'm going to set to 600. I can't go any further than that. We'll have to choose an x scale, a y-min, and a y-max. Perhaps we could set the y scale as well. So let's see. I know the y-min is going to be 0 even before I do any work. Now the y-max, based on some of the numbers that we got on the previous slide, I know that we were getting numbers like 100,000 and we got, I think it was 160,000. I mean, those are pretty big numbers. I think what I'm going to do is, I'm going to guess, I don't know, 200,000. I just want to pick something that's going to go past the previous numbers that we came up with. I mean, it's huge, but we can definitely set it to that. And I think I'll just even leave the y scale at 1. I don't think it's going to be really relevant for us to like see the exact value that's going to, so I'm going to leave that alone. That really just kind of leaves, okay, what should I set my x scale to? So at this point, I'm going to go to my graphing calculator, type these numbers in along with the equation, and see what we get. All right, so I just kind of made a couple guesses here. I entered in my values. For the y scale, I ended up deciding on using 50. It just seemed like after I tried that, it spaced out really evenly in a nice way. I'm going to draw what I see with this choice of window. The graph is equal to 0 here. It's equal to 0 here at both x equals 0 and x is equal to 600, and it's a quadratic. The graph goes up, and then it comes back down, and I'm seeing something like this on my screen. Maybe I'll extend this a little bit. I can see actually that there's this largest point. Here's the max area. It's the greatest point on my graph, which corresponds to some x value, whatever that is equal to here. In fact, it looks like it's directly halfway in between my x-min, which is 0, and my x-max, which is 600, which would be, at this point, just kind of a guess, 300. This is a quadratic, and it looks like this has to be the location of the vertex. So I'm going to go to my table and just verify this guess of mine. So I'm guessing that 300 is where the area is in fact the largest. I'm going to maybe pick some values around 300. I'll try like 290, I'll try 300, maybe I'll try 310 to see if like it goes up and then drops below it. So I'm trying 290. I get 179800. I try 300. I get 180000, and I'm okay. For 3/10, the same thing as I got for 290. Yeah, I'm pretty convinced that this is where the largest area occurs. Now, what does this mean with respect to the problem? It means that if you're trying to build the area, you're trying to build a fence to have the most possible area, a square is actually not the best choice. That's when I chose 400 for the length of that one side of the fence. And the answer is 160,000. In fact, you can do better than that. If you make this side 300 feet, which means this side has to be 300 feet, the other side is going to be 600 feet. So it is this configuration that gives you the greatest possible area, and that area is going to be 180,000 square feet. So that's the max area for this problem. And we got the answer, or I verified it by using a quadratic equation and basically locating where the vertex is. So technically the answer to this problem, I asked for the dimensions. Those dimensions are 300 feet by 600 feet on the adjacent side.